The interpretations of quantum mechanics are varied, including the many worlds interpretation, pilot wave theory, objective collapse theory, relational quantum mechanics, and quantum Bayesianism. Can you briefly list the key ideas and their implications?
You're absolutely right. The interpretation of quantum mechanics is a rich and fascinating area of study, with multiple frameworks attempting to explain the strange and counterintuitive behavior of quantum systems. Each interpretation offers a unique perspective on what quantum mechanics tells us about the nature of reality. Here's a brief overview of the ones you mentioned. 1. Many worlds interpretation, MWI. Key idea: every quantum event spawns a branching of the universe into multiple parallel worlds. All possible outcomes of a quantum measurement actually occur, but in separate, non-communicating universes. Implications: there is no collapse of the wave function. Instead, all possibilities are realized in different branches of reality. Pros: eliminates the need for wave function collapse and provides a deterministic framework. Cons: critics argue it is untestable and philosophically extravagant due to the proliferation of infinite universes. 2. Pilot wave theory, Bohmian mechanics. Key idea: particles have definite positions at all times, guided by a pilot wave described by the wave function. This interpretation is deterministic and avoids the probabilistic nature of standard quantum mechanics. Implications: hidden variables, the particle positions, exist, but they are non-local, meaning they can instantaneously influence other particles regardless of distance. Pros: provides a clear, deterministic picture of quantum systems. Cons: non-locality conflicts with Einstein's theory of relativity, and the theory is more mathematically complex than standard quantum mechanics. 3. Objective collapse theories, e.g., GRW theory. Key idea: the wave function spontaneously collapses at random times, without the need for an observer. This collapse is an objective, physical process. Implications: explains why macroscopic objects appear to have definite states, while microscopic systems remain in superpositions. Pros: provides a clear mechanism for wave function collapse. Cons: the theory introduces new parameters, e.g., collapse rate, that are not yet experimentally verified. 4. Relational quantum mechanics, RQM. Key idea: quantum states are not absolute but are defined relative to an observer or a system. There is no universal reality. Instead, reality is relational and context-dependent. Implications: challenges the idea of an objective, observer-independent reality. Pros: resolves some paradoxes, e.g., Schrödinger's cat, by emphasizing the role of the observer. Cons: some find it philosophically unsatisfying or too subjective. 5. Quantum Bayesianism, Cubism. Key idea: the wave function represents an observer's subjective beliefs or knowledge about a system, rather than an objective reality. Quantum mechanics is a tool for updating probabilities based on measurements. Implications: shifts the focus from what is real to what we can know. Pros: aligns with a pragmatic, subjective view of science. Cons: critics argue it undermines the objective nature of scientific inquiry. Why so many interpretations? Quantum mechanics is incredibly successful at predicting experimental results, but its mathematical formalism, e.g., the wave function, doesn't directly tell us what is really happening in the world. This ambiguity has led to a variety of interpretations, each attempting to bridge the gap between the mathematics and our intuitive understanding of reality. Which interpretation is correct? As of now, there is no consensus. Most interpretations are empirically equivalent, they make the same experimental predictions, so choosing between them often comes down to philosophical preferences. Some physicists prefer interpretations that align with realism, e.g., pilot wave theory, while others favor those that embrace subjectivity, e.g., cubism.